Hey everybody, we're going to look at question 1419 from Bronlome Burston. And this question has to do with kind of introductory kinetic stuff, deals with the rate equation and maybe even a little bit of stoichiometry. So let's take a look here. Part A of this question, it says calculate the number of moles of B that are present at each time, assuming there are no molecules of B at the beginning and cleanly converts the, okay, so basically it's saying, let's do some stoichiometry. So let's do some stoichiometry. Part of what we have to do here is to know that in the reaction, it says that A reacts to B, and that's a 1-to-1 ratio. You can see that right here, A reacts to B. And so because A reacts to B, that means that this initially, ICE, has 0.65065. And so B initially, based on the problem setup, has 0. So that's actually the answer for T when T is equal to 0. The concentration of B is also equal to 0. But now we want to change all these change values. So looking at the data in the problem, it says after 10 minutes, we've lost some amount of A, and now we are at 0.051 moles of A. So that means that this changed by 0.014 moles. Well, stoichiometry says that for however many of these, this here, it's a 1-to-1 ratio. That's what this stoichiometry says. So this is plus 0.014. And so that means that this is 0.014. And so at t equals 10 minutes, the concentration of B is equal to 0.014. And then we can continue to do that same thing every time here in order to get the correct answer. Okay, so we know how much we started with. And so now for 20 minutes, we're going to end with 0.042. So that means we lost 0.023. That means we gained 0.023. So at 20 minutes, the concentration of B equals 0.023. Now I'm not using my calculator here because I can do this math in my head, and it's okay if you can do this math in your head. Okay, so now for t equals 30, we do the same sort of thing. Okay, so that means the concentration of B at 30 minutes is 0.029, running out of space there. And then last, t equals 40 minutes, we do the same thing again. And so that means this is plus 0.034. And then technically that's the amount at the end there. So there's the concentration of B equals 0.0, make sure I put 0.034. And those are all units of moles. So that's part A of that. Now part B says calculate the average rate of disappearance for each 10-minute interval in units of molar per second. Okay, so there's a lot to do in this part B here. First of all, we have to convert to molar, and then we also have to convert to seconds. So let's convert and then calculate. So I'm going to get a new page here, and so this is for part B. And so we have to convert to molar. Remember that molar is equal to moles over liters. And so for part B, let's see, the concentration for each of those is going to be whatever the concentration is, or whatever the moles is, over 0.1 liters, okay, because this is the number of moles. 100 milliliters is 0.1 liters. So now we do the math here. And this time I'll use my calculator. And so now we can continue to go down, and that's at 0 minutes, which is the same as 0 seconds. Okay, so now we do the same thing for all four others of these guys. And 10 minutes at 60 seconds per minute times 60 is equal to 600 seconds. Okay, now the next one. Now that's at 20 minutes, so that's 1200 seconds. And so now the next one, that's at 1800 seconds. Okay, I'm just adding 600 seconds every time. Okay, so now let's see, 3-1. The last one is 3-1 here. Now, what we need to do, now that we've gotten everything in molarity and in seconds, now we want to make sure we answer the question. It says calculate the average rate of disappearance of A for each 10-minute interval. And so just keep in mind the rate of disappearance is, let's see, the rate is equal to change in concentration over change in time. So from 0 to 10 minutes, the change in concentration is going to equal, let's say, 0 to 10 minutes. So 0.065, let's say, it doesn't matter which order we put them in, as long as we put them in both numbers in the same order. So I'm going to go here, so it's 0.65 molar minus 0. What was it? 51 molar. Then it's 0 minus 600. So that change is going to equal 0.14 molar over negative 600 seconds. So now, let's say we get a rate equal to negative 2.33 times 10 to the minus 4 molar per second, which is exactly what you would get, what you were asked for. Okay. And so now we need to do the 10-minute interval between 10 and 20, 20 and 30, 30 and 40. So for 10 to 20. So this side is the 10-second or 10-minute, and that side's the 20-minute. Okay. So now we do the calculator again. So now we do the same thing for 20 to 30. So again, this is our 20-minute and this is our 30-minute data, both on the top and the bottom. Okay, so this is all the information that has to do with 20 minutes. This is all the information that has to do with 30 minutes. Okay, so now we do the math. So now we do the same thing for 30 to 40 minutes. So there is part B. Now for part C of that same question, it says between 10 and 30 minutes, what is the average rate of appearance of B? Well, in order to find the appearance of B, we have to find the disappearance of A. Okay, so let's find the rate of disappearance of A. This is a related rates problem, so we're going from 10. So for part C, we're going from 10 to 30 minutes. The concentration at 10 minutes here, just double check that we get that right, 0.51. So this is 0.51 minus, at 30 minutes, 0.36 minus 1200. 10 minutes is 600 minus 1800. So now B, because it's a 1-to-1 ratio, the dissipant, this is the appearance of A, this is the rate of A, the rate of B is equal to the positive value of that because it's appearing, okay? And now it says, what is the average rate of appearance of B? So there it is. Okay, so that answers all three parts of those questions, and have a great day.